Hello, everyone. This is a great honor to present this paper we did between USC and Carnegie Mellon. It's called HPOD Unsupervised Hyperparameter Tuning or Hyperparameter Optimization for Outlier Detection. It's a joint work between myself and Leman Akoglu, my advisor at CMU. Basically, what's anomaly detection? It's a technique for identify the deviant samples from the general data distribution. And potentially, we use AD and OD interchangeably in this talk. It has a lot of great applications, for example, in traffic accident detection in hydrogen physics, and you can also do this for the medical image to identify the new anomalies, new outliers in the data. And today we're going to talk about how to optimize the hyperparameters in this field. And it's actually this HPOD paper. The motivation is pretty clear. Basically, why do we need to do the hyperparameter optimization for audits? Because for different tasks, you need to select the best hyperparameters, maybe the layers of the autoencoders, that'll be the hyperparameters. And the HPO actually find the optimal set for the parameters for the underlying algorithms. And it's important because OD algorithms are generally sensitive to the hyperparameters, as we can show in here for the LOF algorithm. The default hyperparameter is here, but the best one can be here. And what we can do for the HPOD can give you some hyperparameters here. But if you just simply use the performance by some other algorithms, this can give you pretty bad result. And also for the hyperparameters in the deep learning based algorithm, you can say the performance variations can up to the 37 times, which is really, really huge variance. So because of that, we really need to optimize the hyperparameters for the OD algorithms. And so the problem is that how to identify the best set of hyperparameters for a given unsupervised OD algorithm is non-trivial. There's many challenges. For example, you don't have the ground truth labels for evaluation. You don't have the internal unsupervised loss so that you can optimize that for the good performance. So with that in mind, we define the problem called unsupervised hyperparameter optimization for OD. Idea will be given a new input data set with no ground truth labels. You want to select hyperparameters for a given OD algorithm. So in this work, we introduced the meta-learning based approach for the first time, which means using the prior knowledge to facilitate the HP hyperparameter optimization on the new data set. And the idea will be the following. First of all, what's meta learning? In general, saying you have some historical task, which is called meta train data sets, which you have the labels information for the evaluation. And you have the new tasks, we don't have the labels. You want to choose the best set of the hyperparameters for the specific OD algorithm. You can transfer the best set of hyperparameters here based on the similarity between the historical data sets and your new data sets. Because you can say if the dog and cats, they're similar in a sense, then you can transfer the best information here without doing too much learning thing. So this is the core idea of the meta learning, and we are going to more talk about how to use it for the unsupervised hyperparameter optimization in OD. First of all, we set up the ground saying, can we have a set of historical data sets, n data sets from 1 to n, and they have m different different OD models, as I'm showing on the screen. And finally, you can pair them together so that you achieve the performance matrices. You know each each hyperparameter's performance on each of the data sets. And for the new data set, for the online hyperparameter optimization, what requires that is that you giving the data sets, given the model, you want to identify what's the best set of the hyperparameter. And as you can see, the core will be transfer the knowledge by meta learning. So how to do that? What we're actually doing that is called hyperparameter performance prediction via meta learning. We built something called a proxy performance evaluator F, because the motivation will be the similar data sets will have the close performance given the HPs on the specific OD algorithm. So we can first train on the historical data sets to predict the hyperparameter performance on the new data sets. For example, this app will learn the mapping between the data sets plus hyperparameters to the corresponding performance. This data set part will capture the data set similarity. I mean, this as an indirect way. And how to capture the data sets or how to represent data sets, we'll introduce two techniques here. One is called IPMs and another is called meta features. I will explain this in a second. But with this F-regressor, we can predict the performance of an AP on a new data set without any problem, which is the key. So now let's go back to how to capture the information about data sets. So the first thing we want to talk about is the meta features. So basically, meta features are the core or the statistical features or the summaries of the data set. For example, giving an arbitrary data set, you can summarize its information as a number of samples, features, sample mean, median, and etc. You can also add other informations like outlier detection related features. So with this meta features, you can represent each data set as a 200 element vector. IPMs is called internal performance measures. We introduced it in another paper published a year ago. The idea will be we'll identify some internal measures which are the weak unsupervised thing giving HP, which is weakly correlated to the model performance. Sometimes it's based on the consensus among the different models giving a data set. So with these three things together, so these F models, the input will be the IPMs, meta features, and also the hyperparameters. We can try to predict or learn the mapping between these informations to the corresponding performance metrics. But with this F, we can predict the performance of any HP on a new data set, which is perfect as we need, because we can plug into this for the online model selection stage, the online hyperparameter stage. For example, given a new data set, well, we can sample some hyperparameters and then use F to predict what's the best performance one. You just simply output the best one with the highest predicted performance. That's it. The problem solved. But if you do a close look, you will realize the hyperparameter space is continuous because of the sampling reason. You can sample a lot of different things. There's a lot of combinations. So therefore, we want to identify the hyperparameters which are promising. And so we want to evaluate hyperparameters lambda selectively other than randomly. So what's the promising hyperparameter can be? It should be high performance, which means it should give us a likely good performance. It should also be high potential, which means it should be different from the already evaluated hyperparameters. So there's a trade-off between the performance and the potential. So with that in mind, we introduce something called we adapt something called a sequential model based on Bayesian optimization SMBO. It's a very classical framework. So we can identify the next hyperparameters for evaluation based on something called expected improvement. So it's a measure to give us a trade-off between the performance and the potential of the hyperparameters. You can check more about this in the papers we're having. So using this approach, we can identify the next hyperparameters for evaluation by this EM measures. We can iteratively and efficiently identify the promising hyperparameters to evaluate other than randomly sample a lot of different things. So you can see the key steps in the HPOD will be two stages. So the offline training stage will be learning the mapping between the data sets, among the data set hyperparameters to its corresponding performance, as we're talking about here. Another stage will be the online HPO stage, which means we can iteratively identify the promising hyperparameters using the F. So finally, we can output the best hyperparameters using this two steps. And here's some preliminary or primary results we're having. The baseline wise, we compare with simple approaches and some other more advanced approaches cover the meta learning and other things. The important thing that HPOD is one of the it's only the algorithm which use both the meta learning and can support the continuous hyperparameter optimization. And we set up the test bed on 39 independent data sets. And we also tried this algorithm on 3 different outlier detection algorithms. One is a deep neural network. The two is the shallow or the classical outlier detection algorithms. The key results we're showing here will be the following. First of all, this each of the icon or this small dot represent one baseline algorithm, and HPOD is here. So on this figure, it will show you okay, the performance is the best for HPOD on all 3 different OD algorithms. For many of the times, you will see the performance improvement over some default choices or mean loss will be significant, like over 37%, 58%, etc. So HPOD outperforms all the baselines on all 3 algorithms with a huge margin. And we also tried the pairwise statistical test, and it just give us a result saying it's statistically better than most of the baselines, including some default hyperparameters. So with that in mind, it's a very good and it's a nice and generalizable algorithm for outlier detection, hyperparameter optimization. Thank you.